So in the last video, we said that the Raman spectrum shows the Rayleigh line, which is light scattered at the same frequency as the incoming laser light, and then it shows the Stokes scattered light, so that's at lower frequencies, and then the anti-Stokes are Raman scattered light at a higher energy. And then the Rayleigh line, that Rayleigh scattering, which is as a result of elastic scattering, so there's no net change in molecular energy level. The Stokes-Raman line is a net increase in energy of the molecule, so the molecule absorbs light and scatters it, but it is now shifted from a lower energy to a higher energy, while the anti-Stokes, already in a higher energy, comes back to a lower energy. So that's a net decrease in energy for the molecule. And then each line represents a vibrational state. However, so this from here to here, if it's the particular vibrational state of interest, so that would be the V vibe. So Raman shift, so this shift from the exciting laser line, which is where the Rayleigh line occurs, the difference between, and the observed line. So in this case, so the Raman shift is between this line and this line, or this line and this line. So we see that it's shifted in the same amount of energy as the Stokes or anti-Stokes. That's because we're considering the same vibrational energy level. So the Raman shift is the difference between the exciting frequency and the respective vibrational mode, and that is equal to the V vibe of the molecule, which is energy separation between the two energy levels. It's often reported in wave numbers, but we can have our laser line in wavelengths, so we can easily convert between wavelengths and the wave numbers. So delta V, so this is also supposed to be a delta V equals Vx minus Vi. So let's consider the example. The Raman line associated with the vibrational mode, which is both Raman and IR active, is found at 4600 angstroms when excited by a light of wavelength 4358 angstroms. Calculate the corresponding wavelength in the IR. So first we look at the wave number of the exciting light, which is given as 4358 angstroms, and convert it to wave numbers. So our equation is frequency, not wavelength. So the wave number corresponding to 4600, which was what we observed, is a 10 raised to power 8, 4600. So the Raman shift corresponding to this mode will now be Vx minus Vi, Vi not V naught, which will be 10 to power 8 over 4358 minus 10 to power 8 over 4600. And this gives us, but after a little bit of calculation, 1207 wave numbers. So this is actually the equivalent to the separation in energy level V1, V2. So this difference from the ground state to the vibrationally excited state corresponds to 1200. So we want to determine the wavelength corresponding to this. So it's a matter of converting this back to wavelengths, which is simply this. That's the reciprocal of that, and we have it as 82838. The general selection rule for Raman shift is that the molecule must have a change in polarizability. So remember again, polarizability, that is the ease at which electron cloud can be distorted. It's often represented by the polarizability ellipsoid, or like the inverse of the cloud of electron cloud around molecule. It depends, the polarizability depends on the structure of the molecule and nature of bonds as well. And it's affected not only just by the presence of an electric field, but also by direction. So the way it's affected in this direction is the way it's affected in this direction, where we have assumed that this green cloud is our polarizability ellipsoid. Since this stands for polarizability ellipsoid, it depends. So in looking at the hydrogen molecule along this direction, it looks like a circle, but here it looks like an ellipsoid. So that is that for HCl3. In this direction we have the ellipsoid, polarizability ellipsoid like this. Now when you push the H to the back, you have it almost circular. So this gives a lot of information about the molecule. Okay, so we're going to stop